Hi, in this video, we want to take a look at descriptive statistics for biostatistics. Okay, so what we're going to do, we're going to take the PowerPoint slides from Chapter 2 of Essential Biostatistics, the Cengage textbook by Bernard Rosner, and we're just going to go over descriptive statistics. All right, so the two major things that we're going to talk about, the two biggest ideas that we need to walk away with from this video is one, the idea of central tendency, and second, is the idea of data spread. Okay, so if I want to summarize data so that I have an idea of what's going on with as little looking at the data as possible, typically what we're going to do, we're going to ask ourselves two questions. Where is the data, like the middle of the data? And when I say middle, I'm going to kind of do this. Where is the data located in terms of its middle? And second, how spread out is the data? Okay, so in the first question, we're going to have a measurement of central tendency. Typically, that's either going to be the mean, or the median, or the mode, or possibly the geometric mean. Now, in terms of how spread out the data is, we're going to usually either use the range of the data, the interquartile range, or we're going to use the sample variance. So we want central tendency to tell us where is it located overall. We're going to summarize that with one number. And then we want to understand how spread out the data is. And we're going to summarize that with usually the sample variance, maybe interquartile range. All right, so the first step in data analysis is to describe the data in some concise manner. Descriptive statistics that involve numeric or graphic displays are crucial in capturing and conveying the final results of the studies that you're working on. Features of good numeric or graphic forms of data summarize: they're self-contained, they're understandable without reading the text, clearly labeled attributes with well-defined terms, and indicate principal trends in the data. All right, so here's an example of some graph bars. All right, so vitamin A consumption prevents cancer is the hypothesis that the author is presenting to us with these bar graphs. So their total cancer cases are 200, total match controls is 200. The bar graphs show that the vitamin A consumed by the control is more than that consumed by the patients with cancer. In some cases, the levels exceed the recommended daily allowance. Oh, okay, so we have our cases and we have our controls, and we can see that proportionately we're seeing more with the higher levels of vitamin A. That's what we see. So the bars here indicate that we have more proportionately in the levels with less vitamin A, and here we have very little. Very few in these levels for vitamin A. All right, now here, we want to look at a scatter plot. So the CO concentrations are about the same in the working environment of passive smokers and non-smokers early in the day. This supports the observation that passive smokers have lower pulmonary function than comparable smokers, the non-comparable non-smokers. All right, so let's check this out. Dark is passive smoker. Open circle is non-smoker who works in non-smoking environments. All right, we see that they're about equal. Now look here. We see that the darker one is higher up. We see the darker one is higher up, darker one is higher up, darker one is higher up, and then they go to about the same. And so we can see there's kind of like this trend of the darker being higher and the circles being lower. So this leads us to hypothesize that the CO2 in passive smokers, or the CO in passive smokers is greater than non-passive smokers at these, late morning to early evening hours. All right, so now measures of location. It's easy to lose track of the overall picture when there's just a lot of data to work with. Data summary is important, before any inferences can be made about the population from which we drew the data from. Measures of location is a type of measure useful for data summarization that defines the center or middle of the sample. Now, when I say center or middle, it's kind of like this. Like the deeper you dig into this, the more you'll see that we have conflicting ideas of what the center or middle will be, depending on what's important to you in terms of your data. So first one we're going to talk about is measure of location. This gives us an idea of where is the middle of our data. All right, so let's define the middle with the arithmetic mean, just like you used in what, like 6th grade, 7th grade, something like that. All right, so here we have the sample of birth weights of live-born infants born to a private hospital in San Diego, California during a 1-week period. The arithmetic mean, the sum of all the observations divided by the number of observations, is I'm going to go through, I'm going to add up all the observations, and then I'm going to divide by the number of observations. And so here, we get a number that in a sense gives us the central tendency of our overall data. If I'm looking here, it's, I can kind of get an idea of where the central tendency is, but it's hard to really pick that out beyond the first digit. It looks like it's probably the first digit is a 3, but it'd take a little bit more to get a more precise number. Now, something that's a problem with this is that if I have extreme values in my data, so let's say that there are very small premature infants in this data set, or we have a few really, really, really big kids, the sample average will get pulled towards the extreme values. So in these situations, it may not be representative of the location of the majority of the sample points. Imagine a situation where I have 100 points that are between 1 and 10, and then I have another data point that's 1,000,000. That 1,000,000 is going to pull the sample average to be greater than all but one of the values. So all that first 100 I described to you will be less than the sample average because that 1,000,000 value will pull it away. Now, the arithmetic mean has a lot of theoretical properties that are nice. So as long as we have a non-skewed data set, usually the mean is a good way to go. All right, so the arithmetic mean explained. This funny looking symbol, it's Greek sigma, capital sigma. When I use this, this stands for do addition. All right, so this is the formula notation to add everything up. So I'm going to add up all of the x's. So I'm going to have an x1, x2, x3, x4, x4, x5, x6, 7, and so on. And I'm going to add them all up. This I part is the index, indicates is it the first observation, second observation, third, and so on. And this n tells me where I stop. So I'm going to add up all the values from the first observation to the nth observation. And the subscript tells me which observation it is. So this is the second observation. This is the first observation, and this was our last. All right, now we can always do this over a range of values. So if I go from A to B, so let's say I want to take the third observation, the fourth observation, and the fifth observation, add them up, then this would be 3 and 5. And the sigma implies that we're going to add everything up from the third observation to the fifth observation. So it would be third observation, fourth observation, fifth. And if A is equal to B here, then we just have one value by itself. Now, remember that we can factor out numbers when we're doing addition. And so here, this is just representing that factorization property. All right, so the arithmetic mean has a lot of nice theoretical properties, but if I have extremely large or extremely small values, the mean can get pulled away from the rest of the data, and it's sensitive to that. It's called sensitive to outliers. Well, an alternative to that is to use the median. What I want to do, I want to take the middle value of my data. Now, If I have an odd number of data points, my middle value is just going to be my middle value. If I have an even number of data points, my middle is going to be the average of the middle two. Because it's even, we're going to have, we won't have an exact middle value. So before we can compute the median, I have to go through, I have to sort all the values, and I have to count down the line to find where is the middle. And if I have an odd number, I take the one in the middle, that's the median. If I have an even number of observations, I take the middle two, and then I take the average, add that up, and divide by 2. And so here, look at this data. We can see that this 35 is larger than every other value. I mean, it's more than double this 12. And so if I was to take the arithmetic average, X bar off of this, it's going to be pretty far to the right compared to all but one of the data points. Median is a better choice. Now, which one should you use? Well, the median is good when you have, like these extreme values pulling things over. The mean is good when you have strong confidence that you don't have any data quality issues. If you don't know, go with what your stakeholders prefer. Now, if I have a symmetric data set, so that means that equal likelihood is to the left. If I go like 1 to the left of center, 1 to the right of center, I get about equal probability of that event. If I go 2 to the left of center, 2 to the right of center, I get about equal probability of those events. If I have a symmetric distribution, then the mean and the median will be pretty close to each other. It doesn't really matter which one you use. If I have a skewed distribution, so skewed means that I've got a few values that compared to the rest are extremely likely. All right, when that happens, the arithmetic mean will tend to be larger than the rest of the data set. If I have a skew left distribution, then what will happen is the arithmetic mean will tend to be lower than most of the data set. So if I have a skewed data set left or right, I really want to use the median either way. But ultimately, do whatever your stakeholders want you to do. All right, the next one is the mode. All right, the mode is the most frequently occurring value in your data set. This one is not used as often for central tendency. This is, now if I have like categorical data, such as like states, that, where it doesn't make sense to do addition, or larger, smaller doesn't make sense for, the purpose of our data analysis. Then, the mode tells us which one's the most frequent. The mode frequently can be used in the situation where I only have a few distinct values. If I have like very long decimal point numeric values, the mode usually loses its oomph. It can be a way for us to detect problems in our sampling if we see a value that's coming up far more frequently than we would expect. Now, the geometric mean, the idea here is I take my data, multiply it all together, and I take the nth root of it. So it's the multiplication version of taking an average. And this has some very, very specific uses. Now, if you remember logarithms from college algebra, you'll remember that there's a multiplication and addition relationship between, there's a multiplication and addition relationship for logarithms. That if I have multiplication on the inside of a log, I can convert that to the sum of the individual log pieces. All right, because of that, frequently, if I want to use a geometric mean instead, what I'll actually do is I'll take the take the product and take the logarithm, which converts it into addition. And then we can take an average. And it really doesn't matter which log base you use. Usually we use 10 or E, depending on who our audience is. If you're dealing with statisticians, mathematicians, use E. If you're working with like chemists, engineers, probably base 10 is a better way to go. do whatever works for your stakeholders. All right, so some properties of the arithmetic mean. If I go through and I add the same number to every single observation. So here I'm going through and I'm taking addition. I take every single data point and I add a particular number. Now, if I go and take the average of that, if I take all of the averages after I tack on the number, that's equivalent to taking the average, then adding on that number, like that. And so that's nice. We have a translation relationship. Now, the next thing that's nice is if I take every single data point and I multiply every single data point by the same number, then I take the average. It's the same as taking the average at the beginning, then multiplying by a constant. So that's nice for us. One way that we use this a lot. So let's say that I have temperature in terms of Fahrenheit. I have temperature in terms of centigrade. There's the equation to convert back and forth. Well, if I have the data in Fahrenheit, but I need the mean in Celsius, I can take the mean from Fahrenheit and do the conversion directly instead of having to do a conversion on each data point, then take the average. So this is nice for us. This is the same arithmetic is used in machine learning quite a bit to center and scale our data. All right, so now this should be measure of spread, not speed. Okay, so let's look at these two line plots. I have data point, data point, data point, data point, data point. And now I have 5 data points. If I was to go and take the average of this data, I would get 200. If I took the average of this data, I would get 200. So here, both data sets have the same central tendency. Okay, well, what's different about them? Well, they're spread out more. And so here we can see that this data is far more spread out than this data. Since it's, so these are two very different data samples, even though they have exactly the same measurement of central tendency. So we have more variability in the data up top. All right, so our first way of computing spread of data, the simplest way, is to just take the largest and smallest values and subtract. And that gives us a measurement of how spread out the data is. This works well because it's fast, it's easy to interpret, it's easy to understand, but there is a critical problem. This is relying on 2 data points. If I end up having an outlier or a data error or something weird happens with my data, let's say somebody made a mistake when entering the number, if that's the case, then the range value is going to be thrown off. I have no protection from an outlier if I use the range measurement. So the range is the difference between the largest and the smallest observations. So first thing I have to do, I have to sort my data. I have to put it in order before I can compute this. And this is very, very, very sensitive to extreme observations. Now, also, the larger the sample size, the range is going to grow bigger and bigger and bigger. If I keep on getting more and more data, my maximum value in my data set can only increase if I'm getting more data. My smallest value, my least value, can only get less if I get more data. And so the larger my data size, I can expect the larger the range. All right, so this really isn't the best way to go. It's easy to understand, though. We wish it was better because it would be so easy, but it's not. So we almost never use this. We usually just talk about this in in statistics classes to try and give it as a warm-up to more complicated concepts. So another approach would be to quantify the spread of the data in terms of percentiles and quantiles. Percentiles and quantiles are less sensitive to outliers and are not greatly affected by sample size. All right, so quantiles and percentiles. Okay, so what I'm going to do, I'm going to say, all right, what value in my data has 25% of the data is less than that number? So the 25th quartile is the number that has 1/4 of the data less than that number. The 50th quantile is the data point that has half the data is less than or equal to the data, that one value. And the 75th percentile is the data value that has 75% of the data is less than or equal to that value. All right, and so this is a better way to describe the spread of the data. All right, so quartiles, we break up the data into fourth. Quintiles, we break up the data into fifths, 20%, 40%, 60%, 80%, 100%. Deciles, we break it up by 10%. Now at work, I use vigentiles. I break it up into 5% increments. Now to be able to compute these percentiles, the data points must be ordered first. So I have to sort them, smallest to largest. And then I go through and chop it up. I figure out where the cuts are. Now, if n is large, a stem and leaf plot or a computer program should be used. Okay, if you're doing statistics professionally, always use a computer. Don't bother with a graphing calculator. Get software that is your industry standard and use that. Do not be doing pencil and paper statistics. Do not be using a graphing calculator. Do it the way that your stakeholders will accept it. Be a professional. All right, so we've talked about range and using quantiles to describe the spread of our data. Now, there's another way, and so we can use variance and standard deviation. So the idea here is what I'm going to do, I'm going to look at how far each data point is from the central tendency measurements. Okay. Now, if I was to do that, let's say that I take the difference between each data point and the sample average, and I add them up every single time, 100% guarantee you will get 0. Okay, so that's a problem. So at first glance, this looks like this would be very useful in measuring the spread of the data. The problem is that the numerator is always going to be 0. So what we can do is we could instead take absolute value of the difference between our data and the sample average. And that is what we have here. So this is the mean deviation. All right, so this tells us the average difference between our data and the sample mean. Now, this is very intuitive. This works well for a lot of reasons. I have used this professionally to explain data spread to stakeholders who did not have a strong math background. But we have another option, which is the sample variance. Here we have two ways of calculating sample variance. Both of these have more theoretical properties. So if I'm in a situation where I believe theoretical assumptions are correct, I actually get more information about these guys than I do up here. So these guys, basically the math works out nicely. And so instead of doing absolute value, I'm going to square it to make it positive. Now I can divide by n minus 1. This corresponds to a maximum likelihood estimator or an unbiased estimator. For large data size, it's about the same. If you don't know, go with the n minus 1. That's used far more common. Do whatever your stakeholders, your boss wants to see. Now, the sample standard deviation is where I take the sample variance, take the square root. Up here, if my data is in feet, S squared is in feet squared. So the unit doesn't match my data. By taking the square root, I get things back on the same scale as my original data. All right, now if I look here, look at where the X's are on this line, look at where the Y's are on this line. You'll notice that they're just shifted off from each other. It's the same data, but just in a different spot. Now, if I look at that, has the spread of X, with how spread out the X values are on the line, is that the same as the spread of the Y values? Yes. All right, so what I'm trying to show with this picture is if I have my data and I shift it, I shift every single data point by the same amount, the amount of spread stays the same. Okay, so the difference between the highest and the lowest stays the same, sample variance stays the same, sample standard deviation stays the same. And we also have these nice properties for rescaling our sample variance, sample standard deviation. All right, now the coefficient of variation is that sample deviation divided by the sample average. We use this to evaluate proportionately, do we have a lot of variance compared to the magnitude of our data? Think about if X bar is from the average mass of planets. Well, my standard deviation is going to be absolutely huge, not because my data is really spread out, but because the magnitude of my numbers are huge. And so because of that, this coefficient of variation does a good job of standardizing things, making it easier for us to interpret what's going on. And so here, I have my mean, I have my standard deviation. If I divide the standard deviation by the mean, we see, and multiply by 100, we can see that proportionately, the high density cholesterol has the most spread proportionally. Now, all of these are unitless. Standard deviation is on the same unit as our original data. Sample mean is on the same unit as our data. The division cancels it out. So here, this makes it so that I can compare things, height, weight, triceps, skin fold, all that on the same scale. Now, when the sample size is too large to display all the raw data, data is frequently collected into groups. And we can easily use a computer to do this. You use a computer, don't do it by hand. The frequency distribution is an ordered display of each value in a data set together with its frequency, that is, the number of times that occurs in the data set. When you're giving a presentation, do not show stuff like this. Do not give raw numbers. You're just blasting your audience in the face with numbers. And here, you know, even if I do group it up, I can have too much for my audience to look at. This is too much for them to look at, too much for this to interpret. I need to summarize this better when I present this to my stakeholders. And so what we can do, we can start grouping our data into bins like this. And now we start doing our presentation of the values we want them to see so that we can see, so that we can show them what's going on. So like here, we can see that in this region, these values are occurring most frequently. Now, graphing methods, we think with our eyes, take advantage of that, make a picture, make a picture, make a picture. It's faster to explain to people and to convince people with graphs. Do it. Let the computer do it for you. All right, so bar graphs, we use that to display group data. They're not difficult to construct because we're going to have the computer do it for us, and we can identify sample points within the research. So the original identity of the data point is lost when we do this. Stem and leaf plots. These were, you know, sexy back in the day when people were doing statistics by hand, and we could figure out a lot of information off of it very fast, very easy. I had to do it in school. I wouldn't bother doing it. Now, box plots. I use box plots every week at work. These are great for showing the relationship among medians, upper quartiles, lower quartiles, and they can show skewness and symmetry and distribution like that. And they're easy to compare, which population is bigger than the other. All right, so here's a stem and leaf plot, or two of them at least. All right, a box plot. A box plot is a 5-number summary. All right, I've got 5 values. I have a median. I have an upper quartile, the 75th percentile, lower quartile, which is the 25th percentile. Then I have an upper and lower value that, except for outliers, is the maximum except for outliers, and is the minimum except for outliers here. It's a 5-number summary of my data. I use these every single week at work. Oh, and all right, so how we interpret symmetry and skew. If I see that one of these boxes, if I see that the distance from median to quartile is very different from median to quartile on the other side, I conclude I have a skew distribution. Whichever side has a bigger distance between median and quartile, that is the direction of the skew. I'm trying to hurry through this because the rain is coming. All right, so here, this is specifying what is called an outlier for the purpose of a box plot. All right, so we take the upper quartile, that 75th percentile. Then we take the interquartile range, multiply by 1.5, and take that. Any value above that is called an outlier. If I take the lower quartile, interquartile range times 1.5, subtract, anything less than that is called an outlier on the box plot. And if it's outside this plus or minus 3 range, then it's even more extreme. All right, so what do I see here on these two plots? First and foremost, I see that central tendency medians I see that the bars are cutting into each other vertically. Therefore, I conclude they have the same central tendency. I conclude that the one on the right has greater spread and it has skewed right. This is also skewed right, but to a lesser extent. Here, these look about symmetric each. There's a little bit of a difference, but remember, I can have flukes in my data. These lines are close enough to the middle of each other that I feel like these have about the same central tendency. Scatter plot, we have matched pairs of data, and I use these quite a bit at work. I have 2 numeric variables plotted, one on the x-axis, one on the y-axis. We can change the labels, or the plot character and the color to match another variable. All right, use whatever software your boss wants you to use. Whatever your stakeholder wants, that's the one you need to use. Because if you're using something that your boss is not comfortable with, they'll be hesitant to accept what you're working on. And if they're hesitant to accept what you're working on, they're not thinking about your work. They're thinking about, oh, he used Python instead of using SPSS. Do what it takes to convince your audience of your work. All right, so the 2 big things to walk away with. Measures of location, that tells me where is the center of my data. Measures of spread, measure how spread out my data is. Measure of location, the arithmetic mean, the median, the mode, I never use mode. And then geometric mean for special situations. Measures of spread, standard deviation,